that change as you're kind of increasing your effective total batch size
Yes.
as you add more features?
Right. I mean, in a more detailed slides I had, like in fact the convergence plot, and it does get much more unstable as you increase your mini batch size. And that's why this is challenging. Otherwise, you would saturate this, you would make this as large as possible and push a whole bunch of data into each GPU. Right? But for training, this is not the best thing to do.
This process is frequently confused by the fact that once you get a solution, you don't know why that solution is the best solution. And does anybody ever have thought of going back and looking at layer by layer to see if the solution, if you can identify parts of the solution improving as you progress through the layers to the final output?
Right. I mean, again, as I was saying earlier, these systems are extremely complex. It's very hard to analyze at the level of each neuron, right? We have a billion operations here. So what people have tried to do is they've tried to visualize different images at different layers, like how do these activations look like as it passes through the network. And there, what they see is some neurons are more highly activated towards certain categories than the others. So there's some form of specialization that's occurring, at least visually, that people can see. But there isn't, again, a very clean, mathematical formulation of how we should measure this kind of delineation of functionalities into different neurons or into different layers. Typically, the accepted notion is at lower layers we have less complex features. So think of like lines in different angles, and then they compose together to more complex features as they go through higher layers. Does that?
So it sounds like if you try to analyze one of these, you find that some neurons are specialized for part of it and some are specialized for a different part. If you run it again, two ways they could differ the second time is different neurons could take the same function, and the other way would be the functions divided up into different chunks of neurons. Do you find both? Or is it too?
I don't think anyone has done a methodical study at scale because even this kind of example that I showed, which was demonstrated in a paper, right, is not universal. I mean, it works for some categories. You see this interpretability, for others you don't. Because interpretability is very hard in these systems. You can do it in parts, but not for every aspect. Like we don't have an explanation for every behavior in these systems yet. Great. How am I doing in terms of time?
We're moving along.
I'm already over, so yeah, no, the great questions. I just want to point out that the latest framework is called gluon, from the quantum particle, but also because it's like a glue, it takes the best features from all the previous frameworks and is very simple to run on top, but has all the efficiencies that make it possible because essentially the code that you will be writing is as simple as this, like Python-like code. But what it can convert is into this declarative style, which means it can generate this computational graph that gives the entire sequence of operations. And that's when you can design sophisticated optimization and parallelization schemes once you have that graph. And so the idea is you write, the data scientist writes simple code, but in the back end, magic happens and you get high efficiency.
So you say you support all these imperative languages that then get converted to these declarative. Do you support these kind of already very mature declarative languages like Haskell, which would kind of remove all these difficulties in mapping imperative to declarative in the first place?
Not so far,
Okay.
but there would be ways to, as long as we can have the converter to, we have JSON style, ways to describe these symbolic program, right? So as long as there is a nice converter, we could plug that in. And so that's the summary. right? That the latest framework, I mean, you can think of it as best of both the worlds. It's easy to program, but at the same time gives you high efficiency on hundreds of GPUs. I mean, some of the, I think, largest experiments we did was on 256 GPUs, was more than 90% efficiency in these ImageNet contests. So we have many benchmarks in our system. And so that's, so we've been doing all this in open source. So you can go to AWS and be able to run this. And there is the AWS summit called reInvent that's coming up in 2 weeks. That's a huge summit, more than 45,000 people. And that's where we'll be announcing some new products in the machine learning space. Some of them that I've been working on, I'm very excited about that. So after that, I'll be able to talk a lot more about what those products are. So I think I'll skip the next part, which involved learning into multiple dimensions, but I'll just give a very short overview of what this entails. Right, so everybody agrees that our world is multidimensional. We want to go beyond 2 dimensions. But a deep learning system is nothing but doing a lot of linear algebra operations, right? It's, everything can be finally cast into matrix operations. And what I'm trying to push is, can we go beyond? Why not think of multiple dimensions together? Why not think of tensor operations? And so if you think of an image, its width, height, and channels could be RGB channel. And if it's going through convolutional layers, you're again transforming one tensor to another, right? And so what are the operations that do these transformations? You can also think of them in terms of a tensor and get better functionality and better network compression. So I won't give all the details, but the primitive is just as we think of matrix products, we can also think of tensor products and tensor contractions. You can operate on tensors along different dimensions. And as you keep growing these number of dimensions, you have these increased representational power, you have more flexibility on what kind of operations can be done. To give you an example, this is one of the classic, in fact the first architecture that was run on the ImageNet contest. It's called the AlexNet, and these are the convolutional layers. So you feed in your image, you send it through convolutional layers, and there is this operation called spatial pooling, which is shrinking the size of the image, but it's running it through more filters, so it has more channels. But the last part, you can see what's happening, right? So it's taking this 3-dimensional object and turning it into a vector. It's flattening it. And so you're losing information about the spatial dimension beyond the stage. And so what we did was saying, why not do tensor operations even here, right, all the way to the end? Like, why should we convert them into vectors? And it turns out you can have a much smaller network. You can save space in terms of the number of parameters by a huge amount while hardly reducing performance. And so this was in fact our first foray into asking, if we kind of think of adding tensor operations to different parts of these networks, different kinds of architectures, how can we strengthen them? How we can exploit these dimensionality information better? So I will skip these. This is all the hardware, how we can make them better as well. And the other aspect we've been working on is how we can use tensors to also exploit multiple different kinds of data. If you have image data and text data, and you want to jointly process them, right? So in this example, you want to answer a question about the image, right? So in this case, you want to combine features from text and image efficiently. And so tensors will also help us naturally encode this and naturally think of higher order moments across image and text. Again, the details are in the papers, but intuitively what tensors are good for is to exploit different dimensions in data, exploit different kinds of data together, and have flexibility in how we want to compress them, what kind of transformations we want to do with them. And so I see like tensors really being the future, taking the current matrix-based deep learning systems further into more dimensions. And so that kind of also relates to my earlier area. I started out thinking about tensors to use for learning hidden variable models and to do large-scale processing. And that was this example, as you can see, it dates back to 2012. The question I was asking was, given a set of documents, how we can exploit the information of how words occur in a topic to learn what are the topics in the document. So if you're just given a bunch of documents, but you're not told what each document is about, there are no labels, right? This is a very hard task. But just based on frequencies of how words occur, this tensor method is able to learn what the topics are. So the intuition is, if you look at how triplets of different words occur together and try to factorize the tensor, that tensor has hidden information about what is the distribution of topics. And based on that, you can very efficiently come up with each document, like what topics it contains, and do it at scale on millions of documents. So I want to conclude. I know I covered a lot of topics, and I also am very happy to see a lot of engagement and interaction, and many hard questions that I don't know the answer to, or none of us do. But that's what I think will keep this field very interesting. We have, right now we are at the cusp. We have very good programming tools, MXNet and